The next speaker is Professor Tang from the Department of Earth and Atmospheric Sciences. So take it away.
All right, thank you. Good afternoon, everyone. I guess we'll be switching gear a little bit. I'm a biogeochemist by training. So we look at the biology and chemistry of geological materials, basically natural materials, if you can imagine rocks and minerals. And what I'm going to talk about today is more about how we can characterize these very complex and heterogeneous materials using a multiscale approach, and also how we use the approach for implications for resource recovery, which might be more relevant to those of you who are sitting here. So this is basically what we do in our lab. We look at what we focus on is interface processes. So we look at the mineral water interfaces, but this is really sitting at the interface of many different disciplines, such as earth science, environmental science and engineering, material science, chemistry. We also work a lot on planetary materials and also ocean science related problems. But the core concept is really looking at the speciation, or if you say structure reactivity correlation. We go from the bottom up approach. We look at the very small spatial and time scale, and then try to use the information that we learned of these chemical processes, their kinetics and their mechanisms, to try to extrapolate to larger scale processes and understanding and explain what might happen in natural or engineered environments. So what we focus on is really looking at the biogeochemical cycling of elements, such as nutrients and metals, critical metals, as what I will be talking about today. We look at the fundamentals, such as microbe-mineral interactions. We look at fundamental of contaminant fate transport, remediation methods, and how stable these remediation products might be. And also look at planetary surface evolution, such as what might happen in the oxygen atmosphere on Earth and Mars. But on the application side, like I said, we look at these fundamental molecular scale processes and try to use them to rationally determine or design application processes or techniques, such as looking at element speciation in complex matrices and use them to for insights on resource recovery. And we also work on the development of synchrotron X-ray techniques, microscopy and spectroscopy techniques. So first, I want to define a little bit terminology, which might be more familiar for those who work with natural systems, where we look at the speciation. So here by speciation, we're defining them as the chemical and physical state of an element. So imagine a chemical state would include their mineralogy, their phase, their oxidation state, local coordination environment, and the physical state would be their correlation with other materials or other elements, such as their association with specific elements or mineral phases. And this speciation is really important for understanding the mobility and bioavailability or toxicity of specific elements in natural environment, and then ultimately determine their fate and transport and how we might be able to design remediation strategies. And now, if you think about speciation, these are the, like I said, molecular scale mechanisms that we typically look at, such as absorption in a sphere or outer sphere, or some people call it chemosphere of chemoabsorption or physical absorption, chemical absorption or physical absorption. We can also look at the surface precipitation, incorporation, co-precipitation of elements with other solid phases, or looking at abiotic or biotically mediated redox reactions, such as those involving minerals or microbes. So I just want to give you an example of why speciation is very important in understanding natural materials. If you think about chromium, many of you would think of, oh, chromium is a toxic metal. But if you really look at the oxidation state or the speciation of chromium, you will see chromium-3. This is the very insoluble and low mobility phases. It typically exists as this green precipitates if you look at it in nature. And so because of this low solubility, it has very low bioavailability. There is actually also an essential nutrient that you can find at the drugstore. If you go to CVS, you will see chromium supplement. But if you think about the other species, chromium-6, it's highly soluble and highly mobile. You see them, there will be this very bright yellow dissolved phase. This is what's typically contained in wastewater, chromium contaminated wastewater. And it has high bioavailability because it has this tetrahedral structure, which is very similar to phosphate structure. It's highly toxic and carcinogenic. So if you really want to think about chromium remediation or toxicity, maybe we should also talk about speciation. And California actually just in the past few years passed the state's first law of defining or regulating toxic metal concentration by looking at the exact speciation of chromium instead of, because EPA typically regulates the total concentration for many elements, but that was the first state law regulating a specific speciation as chromium-6. So in order to understand how this different speciation would affect the large scale or microscopic scale processes, we really need to take a multiscale approach. So looking at the molecular scale, oxidation state, local coordination environment, microscopic morphology, element distribution, element phase association, and then moving on to thermodynamics and kinetics, and then field scale mobility, fate, and bioavailability. So we use a lot of synchrotron X-ray techniques such as spectroscopy, diffraction, scattering, and micro X-ray fluorescence mapping combined with micro X-ray absorption spectroscopy, as well as other microscopy and spectroscopy techniques such as SEMTM, XPS, and NMR. I just want to give you another, or I think I'll be focusing on this example of rare earth elements, which might be of interest to many of you. You probably already know that rare earth elements are defined or nowadays called as critical materials for sustainability. And they have some unique properties. So when we talk about rare earth elements, we're actually talking about this whole row of lanthanides, and including some scandium and yttrium because they have similar properties. But this whole row of elements, they have very similar chemical properties. And so they have very similar behavior and they coexist typically with each other. They typically exist as trivalent oxidation states, except for cerium and europium in certain conditions. And we can divide them into light REE or heavy REE elements depending on their chemical properties. And they are very important for very wide range of high-tech applications. But the problem with rare earth element or their supply, if you think about, or if you look at rare earth concentration in Earth's crust, is actually not that bad. It's about 200 ppm, which is similar to copper and zinc, which we worry, but we don't worry that much. But the problem with rare earth or the problem with REEs is that they tend to be very dispersed in all types of minerals. So they don't readily form mineable ores. In other words, you find them everywhere. They can be occurring as accessory elements, but they are not typically mineable. And another kind of national security issue is right now, China accounts for about 85 to 95% of global REE production. And right now, the US doesn't have a full production chain of REE. There are only two locations. One is the resumed Mountain Pass site. Another is actually in Georgia for mining of specific REE containing minerals, but there is no complete production or manufacturing chain in the US right now due to the very heavy environmental pollution associated with the production. And right now, more than 80% of REE in the US used are imported from China. And because of all these concerns, the high demand of REE for high tech and sustainability and energy, on the other side, potential disruption of supply chain. So there are really growing interest in first exploring domestic REE deposits, geological deposits, as well as non-conventional alternative resources such as coal fly ash, municipal solid waste, incineration ash, spent magnets, electronic waste, phosphor gypsum. There are also, at the same time, development of sustainable extraction and processing manufacturing technologies that are environmentally green and also sustainable. So what we will be talking about today is about mining or extracting REE from coal fly ash. I'm not going to go into the details of the coal burning process, but what you can learn about is during coal burning at high temperature, there's about 10% of non-combustible mineral matters that remains, and a large portion of them are collected as fly ash. And in the US, about 45 million tons of coal fly ash production annually. Now, coal fly ash, it's actually considered as an emergent REE source, as well as many other different alternative resources as I just talked about. So the opportunities with coal fly ash, REE extraction from coal fly ash, is the relatively high REE concentration. So the total REE concentrations are about 250 to 800 ppm. As you remember, we talked about REE concentration in the crust as 200 ppm. It is a reliable source. There is massive reserves in legacy disposal sites. Even if we stop burning coal right now, there's still a ton of coal ash that we can work with. And there are right now continually about 45 million tons production annually. There's negligible mining costs. If any of you work with mining industry, you would know a huge portion of mining, or the most energy and emission intensive part, is grinding. So when you mine rocks, you need to grind them into processable fine powders. And that's the part that's most energy intensive and costs most of the CO2 emission. So by working with these already fine materials, we can eliminate the mining costs and associated CO2 emission. And there are a lot of environmental and economical benefits as well. On one hand, we're trying to extract a useful and critical resource, but on the other hand, we're also trying to deal with or manage a solid waste that has its own problems. So if we calculate the potential annual value of coal ash derived REE, it's about 4 billion in the US. But of course, there are a lot of challenges, as you can imagine. So on the REE recovery side, we really need to understand the REE speciation, distribution, and extractability in coal ash samples, and also how we design, as I mentioned, selective extraction and recovery technologies. As you can imagine, we are trying to extract something that's only at a couple hundred ppm, but you still have a lot of residual materials that you need to work with. And on the other hand, from the waste management side, you also need to minimize the secondary waste production. You don't want to take one waste, produce something, and then produce another secondary waste that you have to figure out ways to treat. And also we need to develop some method that's green and sustainable with low environmental impact. So what we try to do is really, like I said, from the fundamental aspect, we try to understand REE speciation, distribution, and extractability in coal ash by characterizing the REE speciation change during the heating process, as well as the REE in coal ash themselves. And also understanding what are the interfering metals in coal fly ash that might interfere with our different extraction methods, and then rationally design our extraction method for a closed loop treatment system. And here by closed loop, I mean, we want to extract REE or useful product, but at the same time, we also need to deal with what's left over. We don't want to produce another stream that's also toxic and with environmental hazard. So let's first look at REE speciation change during coal burning process. So the approach we took is to start with pure REE compounds. Here we took 12 common REE-bearing phases, such as organic complexes, REE carbonates, REE phosphates, and REE silicates. These are either synthetic or natural materials, pure, and we heat them and then cool them down. And we want to understand what happens to their mineralogy and oxidation stage, which would approximately tell us what might happen in coal fly ash or the coal burning process. I'm not going to go into details about how we look at all those 12 compounds, but I'm just going to show you two examples. The first example is REE lignin complex. So lignin, as you might already know, that it's a very common biopolymer in most plants, and it's an important substance for coal formation, and it represents REE organic complexes. So when we heat it up, we look at TGA and we look at in situ X-ray diffraction. This is actually in collaboration with Dr. Hailong Chen, who just talked about in situ XRD. So we heat the samples up and then cool them down, and then we monitor the change in mineralogy during this process. What we found is REE lignin complexes, they decompose at about 300 to 1,000 degrees C, and there's about 10% residual solids, and all the REE lignin complexes are transformed into REE oxides. Not surprising. And then we look at monazite, which is on the other end of the spectrum with no transformation. So monazite is a very common REE phosphate mineral, and it's also observed in coal. And as I mentioned, there's no significant weight change or decomposition transformation along these heating processes. They remain in their REE phosphate structure. So these are the two ends of the spectrum. And then we further take a look at synchrotron X-ray techniques. So we use these techniques for our later characterization as well. So we'll use bulk X-ray absorption spectroscopy, which is an element-specific technique instead of XRD looking at the bulk evolution. Now we're looking at a specific element, in this case REE. We can look at the oxidation state structure in situ. It's non-destructive method. It has high resolution, can detect down to very low ppm samples, and is highly desired for complex heterogeneous samples in our case. We also combine our bulk results with microfluorescence imaging and micro X-ray absorption spectroscopy. In this case, it's like a raster scan of your samples, as the previous speaker mentioned. You can look at the elemental speciation, but then you can pick hotspots or individual particles that contain high concentration of your REE, focus on those specific particles, and then look at the REE speciation, oxidation state and structure within that specific particle. And depending on the beamline you go, the resolution can vary. You can go down to nanometers or several microns, also, again, depending on your needs and the beamline you go. So when we look at the REE oxidation state by bulk XAS in these reacted samples, what we found is, remember I mentioned that most of the REE exists in trivalent state, but cerium has another different oxidation state, cerium-4, and they do show very different spectral feature. And we can look at our samples before and after the heating. And by combining all this information, what we found is that the REE speciation in coal, or these 4 groups of REE phases that are typically occurring in coal after heating and cooling processes, organically associated REE, so REE organic complexes, they become REE oxides with oxidation, so cerium being oxidized to cerium-4, REE carbonates, again, decomposition to become REE oxides, cerium oxidation into 4, REE phosphates, and REE silicates stay intact in their own structure without observed cerium oxidation. So those are pure compounds, pure model compounds that we looked at REE transformation during heating and cooling. And now we're going to move on to very complex stuff, which is coal fly ash. It's very complex from many different perspectives. So particle size, we're looking at 1 to 100 micron in particle size. And we're looking at very different morphology. So you can very commonly observe amorphous phases or crystalline phases. You can have spheres or cenospheres, which is basically a hollow sphere, or you can have narrow spheres like what you see here, which is spheres in spheres. Because during the cold cooling process, some of your glass, they might just encapsulate and recondense or reprecipitate. And now another side of the complexity comes from the chemistry and mineralogy. For coal fly ash, we typically divide them into class C and class F ashes. And the main difference is on the silicon, aluminum, iron oxide, and also calcium oxide content. So as you can see here, class F ash contains more silica and aluminum oxide versus class C ash contains a lot more calcium oxide or calcium containing mineral phases as well. And as you will see later, this actually makes a huge difference when we try to extract REE from these different types of ash. And another complexity is really the low REE content. We're looking at a couple hundred ppm of REE. And remember, this is a whole group. And the highest concentration ones that we're looking at cerium, neodymium, lanthanum. So what I thought would be very useful is to look at the speciation, like the methods I mentioned to you before, the physical distribution, and then try to compare that with their extractability using acid leaching, sorry, that should be leaching, and also sequential extraction methods. But for my students, it's really a lot of luck and a lot of patience. So, but if we can combine all these different information from different scales. As you can see, this is really from molecular scale, and then moving on to microscopic and batch scale information. We will be able, hopefully, we will be able to develop a more systematic understanding of REE in coal fly ash. So now moving on to look at REE speciation at the microscopic scale using SEM. What we can observe under SEM EDX is we can see REE as major elements, so such as the existence of monazite and xenotime, two different types of REE phosphate minerals. We can also see them as trace elements, such as incorporation into zircon and lime and also other mineral phases. So that's just another level of complexity of speciation that you're looking at. They also distribute very differently. So we see them distributing. So in this case, you are looking at, this is where they are located kind of on the edge of a large particle. But in this case, you are looking at them as an inclusion here in a glass phase. So taking all the information together, what we think is happening is during the heating and cooling process, you can have aluminosilicate minerals such as clays. They will melt and then solidify to become glass phases. And on the other hand, you would have REE phosphates and silicates. Remember, these are the ones that they do not really change during the burning and cooling process. So they would just retain as themselves and then becoming REE-bearing phases. But the complex part is they can be captured into the glass phases and become encapsulation. So now if you think about what you're going to do to try to extract them from these encapsulation phases, that's going to be a challenge, or they might behave differently. And now moving on, looking at the microscopic speciation, now we want to look at a bulk, at the bulk global level, looking at to quantify their speciation. We know there are phosphates, carbonates, oxides, or other REE minerals, but how do they occur at a global scale in these samples? So the method we took again is X-ray absorption spectroscopy. We took a very big database of all different kinds of REE occurring natural minerals or natural phases. We use yttrium as a fingerprint for all the different REE minerals or all the different REE elements because yttrium has a high concentration and its spectral features are typically more distinguishable. And we run the same, we took the Zane's spectra of the unknown samples and tried to do a linear combination fitting to quantify the presence and relative percentage of different REE species in our coal ash samples. And this is we come up with. So we have a lot of oxides. We have a lot of REE existing as phosphates or doped in apatite, another calcium phosphate mineral. We also have REE that are doped in iron oxide minerals. So again, the take-home message now into a real complex matrix. We have the organic associated REEs are not stable. REE carbonates are not stable. Phosphates are stable, and we can also have iron oxides that can enrich REE through absorption or incorporation processes. So now we understand how REE transforms during the cooling and burning process. We also understand the heterogeneity or the complexity of REE in coal fly ash, both from the chemical forms and the physical distribution. Now we want to test their acid extraction extractability. A very first step that we do is we conduct a thermodynamic calculation using a software called REEs. So we calculated the solubility of different RE phases along different pH region. Here is pH 0 and that's 10. It's kind of reversed. And what we can find is we can define them or categorize them into 4 different mineral groups. RE oxides and carbonates, they tend to dissolve. This is only acid dissolution. They tend to dissolve within pH about 3.5 to 5.5. Apatite dissolves at about 1.5 to 3.5. RE phosphates and hematites requires more acidic condition. Zircon and glass, those are typically the residual phases that are very hard to dissolve. And then we test acid extraction of our coal fly ash samples, and we actually saw similar trend. Remember, our samples has a lot of oxides and a lot of phosphates. And our Class C sample, Class C fly ash, has more calcium than silica. right? So we saw much higher extraction from class C fly ash than the class F fly ash, which indicates that the glass phase encapsulation mechanism is very significant in preventing the extraction from class F samples. So this is what we're deriving as a speciation distribution extractability correlation. We have REE occurring in iron oxides, phosphates, oxides. They might exist as encapsulated REE-bearing particles in glass phases, which is more common for class F, or they might be existing as discrete REE-bearing particles, which is more common for class C, which also results in their different extractability under acidic conditions. So now what's next? So based on what we know, now we can think about, okay, we might be able to do density separation because monazite and xenotime-based REE phosphates, they are pretty heavy. You might be able to do density separation to separate them out. Class C versus class F, you might want to use class C samples because they have lower silica content and higher extractability. Or if you want to use class F, you might want to think about alkaline pretreatment to remove the glass phases in class F. So the challenges are REE extraction. Well, we want to leach them out. And now we know the oxides, we know the specific phases, and we know how REE typically works with different organic ligands. So our concept is to use low-cost and biodegradable organic ligands that can facilitate oxide or phosphate dissolution, and also with preferential complexing capability with REE to leach them out and then separate them from the other interfering heavy metals. But we also need to think about wastewater and the solid residue produced from all these different processes and try to minimize the production of these secondary wastes. So what we came up with, we started testing with citrate. And we worked at pH 4 and pH 7, so staying at kind of neutral pH range because we don't want to produce very acidic acid wastes. You can see without citrate, class C and class F extraction at pH 4 is about 5 to 20%, and citrate really enhances it to about 10 to 60%. Against class F is not really behaving very well here. And based on thermodynamic calculation, we know that the major REE species are REE citrate complexes, as we predicted. But as some other interfering metals, such as iron, aluminum, and zinc, copper, they are also leached into the solution. So we come with coal fly ash. We add in citrate as a relatively neutral condition, came up with a REE enriched extraction solution. And now we need to worry about downstream separation of REE from the other interfering metals. And what we decided to do is to use oxalate. REE oxalate has a stronger stability than citrate complexes, and it tends to precipitate. So when we add in oxalate, very interestingly, we saw all these other heavy metal, divalent metals retaining in the solution phase, but REEs are precipitated out as a solid phase. And again, this is consistent with thermodynamic calculation. We calculated the system to be oversaturated with calcium oxalate, and which is confirmed by XRD and SEM. So what we think is happening is you have a calcium REE oxalate co-precipitate. And the good thing about this is we can then calculate the enrichment factor. So with this calcium REE oxalate product, we are enriching the REE content by about 2 to 4 factors, or 2 to 4 times of the previous coal fly ash sample. So this relatively pure REE oxalate product can then be used for downstream processing or separation. But then we are left with a lot of solid and liquid residues from the previous extraction and separation steps. And we combine all of them to synthesize zeolite. So at the end, we end up with sodalite, but the phase can change depending on the concentration and also specific reaction condition. But typically we get zeolite group minerals, which is very effective in immobilizing all the heavy metals from the coal fly ash. So what we end up now, this is the last slide. So we start with coal fly ash. We take citrate, separating it into extraction solution as solid residue. Extraction solution further down oxalate precipitation to produce a calcium oxalate product that is relatively pure and high concentration. Our solutions and all the solid residues from the previous step, we produce them into zeolite. And all the heavy metals from the coal fly ash are now stabilized into the zeolite. We have two different products, and it's a very big, I think it's about 80% volume reduction for the solid wastes. And you have relatively low chemical inputs and low energy inputs. But the information or the idea that I hope I have conveyed to you is really looking at the molecular scale speciation, taking a multiscale approach experimentally, theoretically, try to understand the physical and chemical speciation and distribution and correlate that with the batch scale or larger scale extractability for the rational design of a green method for REE recovery. And obviously, we're taking similar approaches also to look at REE bioweathering in geological cycle, biomediated transport and occurrence, and also redefining REE system for tracing geochemical processes, both in modern and ancient history. And the engineered approach where we are expanding this approach not just on coal fly ash, but also on municipal solid waste, incineration ash, electronic waste, and spent magnets. And this is just acknowledge of my group and the funding resource. And that's it. That's all I have.
Thank you so much. Any questions? I'll sample Professor Wilkinson question.
So to my untrained eye, when I was looking at your library of yttrium-zane spectra, many of those look very similar. So I imagine if you were doing a straight least squares fit of 10 components or something, you'd have lots of horrible correlations, negative values. But what's your approach to avoiding that and kind of getting down to a small number of species that might really represent what you have?
That's an excellent question. We had a lot of difficulty, as you can imagine. So first, we also looked at Syrian, neodymium, and lanthanum model compounds. Their spectral features are not as distinct as yttrium, and also based on literature. So that's the reason that we choose yttrium as a fingerprint to represent the whole group of REE. The next question relates to how we actually kind of distill down to different groups of REE model compounds. So the approach we took is we first, obviously, we tried target transformation, tried to look at the different components and their suitability as a representative end member. And then we individually add in different components. And we only include the components if the goodness of fit is reduced by 10% or 20%. Then we include it. But then many of them are, so for example, you can say monazite and xenotime, they're both phosphates, but they have different structure. So we include them as one group of phosphates. So we have, it's like a lump sum number. So that's why at the end, what you have is, oxide is oxide. But for phosphates, basically, we have to lump sum some of the different phosphate phases. And also iron oxide here, we're also including them as low or dope species. So group them into big categories. Anything that's less than 10%, we pretty much discard them as a noise.
Excellent. Any other questions? Well, if not, in the interest of time, thank you again.